Yeah, my name is Xinzhou, and I am a PhD student in Jessica's lab, and currently a fifth year student. So I'm graduating this summer, and this is my current research work called Clipper. And it's very great to have this chance to share my research experience with you. So when I introduce my project, feel free to ask any questions, or if you find anything hard to understand, you can just tell me so that I can go to some more details. So the name of this paper is Clipper p-value free FDR control on high throughput data from two conditions. So you may find this title having too many concepts that you are not very familiar with. So don't, and I will go to the details of these concepts so that I hope you can at least understand what I am doing after this talk. So first, let's look at these concepts. So in the title, we have these concepts. First, high throughput biological data, and then two conditions, and then fourth, discovery rate control, and then p-value free. So first, I would like to introduce our data, which is the high throughput biological data with two conditions. So here is an example of the high throughput biological data. So from this cartoon, we have two conditions of data, condition 1 and condition 2. And in most example, the one condition is called the experimental condition, and another is called control condition. So for example, the experimental condition can be some patients with cancer, and the condition 2 can be some normal people, so that they don't have cancer. So these are two conditions of people, and within each condition we have a matrix. In this matrix, so each row is a patient. So here we have 3 patients for condition 1, condition 2, and 3 patients for condition 1. And for each column, it is a gene, and it is the measurement of the expression level of the genes. So we can see from this legend, a red value means high expression, and the blue entry means low expression. So here, the high or low may mean how active each gene is. If the gene has high expression, for example, this gene here, all these 3 patients have red or high expression for condition 2. But so it may mean that these patients, or the gene in these patients are very active. And if we look at the condition 1, we can see that for the same gene, this gene is not so active in condition 1. So if we look at this figure, so we can see the expression values for condition 2 are higher than the expression values for condition 1, so that we can see that this gene may perform differently between the two conditions, or if the two conditions are cancer and non-cancer, it may mean that this gene has some functional relationship with the cancer. So if we want to identify whether a person have cancer or not, maybe we can look at this gene as an indicator. So this is why the gene expression analysis is very important, because we can look at the two conditions and look at the genes that perform differently between the two conditions. And if we look at this gene, we can see that all the patients have equally small expression values under the two conditions. So this gene does not perform differently between the two conditions. So this gene may be not so interesting in our analysis. But this gene is more interesting because the cancer patients and non-cancer patients have very different gene expressions on this gene. So is this clear to you? So this example. Okay, if you don't have any.
Yeah, please ask questions. If you think this is not making sense to you, please feel free to raise your hand or directly unmute yourself and ask.
Yeah.
Okay, so Xinzhou, whenever you ask a question and you don't hear any response, maybe in 5 seconds or 10 seconds, yeah, wait for longer, then you can continue.
Okay.
Yeah.
So here we call. So here we can see that. So if we call each gene a feature, then we have a large number of features here, but a small number of samples for each conditions. So here we have only 3 samples for each of the 2 conditions, but we have very large number of samples, and this large number of large number of features. So this large number of features is what this high throughput means. So the high throughput means a very huge number of features. So in people, in human genome, there are about thousands of genes. So the number of features will be very large. But as the expands to get the measurement of one patient is quite high. So we usually have small sample size, which means that we have small number of patients. So this is how our data look like. These high throughput biological data usually have large number of features but small sample size. And we would like to compare 2 conditions, one experimental condition and one background or negative control condition. And we want to identify the interesting features, for example, such genes, by comparing these 2 conditions. So in this example, we may see the first gene may be interesting, and these genes may be uninteresting because they are very similar between the 2 conditions.
I had a quick question.
Yeah.
So why do we, is it like necessary to use like a small sample size, or are there like benefits to using like a larger data size, larger sample size, and having like multiple people who have like condition 1 and multiple people who have condition 2?
Yeah. Very good. I think it's a very good question. So it is always good to get a larger sample size. So because with a larger sample size, we can always get better statistical inference and make more reliable results. But the fact is that it is very expensive to get all the expressions for all the genes for one person. So due to the limit of the expense, we can only get a small sample size, and that is the question.
Thank you.
Yeah, you're welcome. And here is another example of the high throughput biological data. And this is, this one is called the differential express gene analysis, and this is called the p-calling analysis. So from this p-calling analysis, this is an example with only one sample for each condition. So here we have the first condition is the experimental condition, and second is the background condition. So in this example, each feature, so which correspond to the gene here in this example, each feature is a genomic region. For example, the yellow beans here. So each bean is a feature, and within each bean, we can see there are some peaks in each track, and these peaks are the intensity of some genomic signals, so biological signals. So we want to identify those regions which has higher signals in one experimental condition and have small signal intensity in the background condition. So if in this region, for example, this yellow beam region or this red region within this red rectangle, so we can see that the experimental condition has higher signal intensity than the background condition. In this case, we call this one a peak because the experimental condition has much higher intensity than the background condition. So or for these regions, we can see they have very similar intensity between the two conditions. So we don't call it a peak in the experimental condition. So this is called peak calling. And in this example, we only have two samples. So we only have one sample for each condition, and each feature will be a bin here. So we can see that in real biological analysis, the sample size can be very, very small, even one sample for each condition. And but on the other side, the number of features can be very, very large. So how can we identify these interesting features, these peaks in this example, or these genes in this example? We have different ways to do this. And before introducing how we identify interesting features, maybe you can first categorize the two kind of interesting features as enriched or differential. So here, enriched feature means that the experimental condition has larger values than the background condition. For example, in this peak calling analysis, as we only look at the peaks in the experimental condition. So the only interesting peaks are those that have higher intensity in the experimental condition than the background condition. And another category of the interesting feature is called differential features. These features are those features that have different values between the two conditions. So they can be either have larger values in experimental condition or in the background condition. So for example, in this example, this gene has higher values in condition 2, and this gene has higher values in condition 1. So both genes are interesting because we just want to look at the difference between the two conditions, and we don't care which condition has higher values. So for this kind of interesting features, we call them differential, and for this kind of features, we call them enriched. So, and in fact, these two kind of features correspond to the two different alternatives in hypothesis testing. If you are familiar with hypothesis testing. And then I'd like to introduce the false discovery rate control. So before introducing false discovery rate control, I would like to have a review of the hypothesis testing and p-values in case you are not so familiar with these concepts. So in fact, we have introduced these in the seminar 2 weeks ago. So hypothesis testing was used to test whether the null hypothesis should be rejected or not. So and there are some basic components of the hypothesis testing, including the null hypothesis and the alternative hypothesis. And we also have a test statistic, which is a function of data. And we should know the distribution of the test statistic when the null hypothesis is true. So in this example, if we come back to the gene expression example, one null hypothesis is cancer people have the same mean gene expression level as the normal people, which means mu1 equals to mu2. So, and the alternative hypothesis can be cancer people have a higher mean gene expression level as normal people, which is mu1 greater than mu2. In fact, we can change the alternative according to our interest. For example, if we think the two the alternative can also be cancer people have different gene expression level as the normal people. In that case, the alternative will be mu1 not equal to mu2. But in all cases, the null hypothesis will be still be the same, mu1 equal to mu2. And if we have taken the stats 10 course, or if you have heard about this, there is a test called two-sample t-test. It is something that can test whether two samples have the same mean. So if we look at one gene and look at the expression values for the patients from the two conditions, we can do a two-sample t-test. And in that case, the test statistic will be the t statistic, and the null distribution of the test statistic will be t distribution. And then some other components of the hypothesis testing include what is considered more extreme and a significant level, and the p-value is calculated as the probability that the test statistic is more extreme than the observed value t given the null hypothesis is true. So if we come back to the example, so if this is the null distribution of the test statistic, so it is a t distribution. What is more extreme will be dependent on whether it is a one-sided test or two-sided test. So when the alternative hypothesis mu1 greater than mu2, then the more extreme part will be the upper tail. And if the alternative hypothesis is mu1 not equal to mu2, then the more extreme part will be the two tails. And then we will look at the proportion of the tails according to the definition of more extreme, and then we will get a p-value. And finally, we will compare the p-value with the significant level alpha, which is a preset small value, for example, 0.05, to make our conclusion. For example, with one gene, we can get the values from the two conditions and then calculate the t statistic and then get the p-value of that t statistic and then compare that p-value with the 0.05 threshold. When the alternative is mu1 greater than mu2, we calculate the p-value by calculating this upper tail. And if the alternative is not equal to, or when the interesting features are differential features, then the p-values are calculated by looking at the two-sided proportions. So do we have any questions about the hypothesis testing or p-value framework?
Yeah, so just to add to Xinzhou's slide, we can consider p-value just as a transformation of your data. So given your observed data, once you apply the procedure Xinzhou just described, you're going to convert your data into a number between 0 and 1. That's the p-value. And what it means is that the p-value presents some evidence against your null hypothesis. And so here the null hypothesis Xinzhou said is mu1 equal to mu2, which means that you believe your data from two conditions are having the same population mean. So in other words, the smaller the p-value, the stronger the evidence you have against the null. So that's why we always say when the p-value is less than a threshold, we would reject the null hypothesis. But the key is to think of the p-value as a number that is directly transformed from your data. Okay, so Xinzhou, please continue.
Okay, so we will reject the null when the p-value is smaller than 0.05. So if we go back to the null, it will reject the null, which means that we reject that mu1 equals to mu2. So which means that we may think that this gene is interesting because we reject that mu1 equal to mu2 for that gene. And then we may think that gene is interesting and we may call that gene as an interesting discovery. But however, we may have some problems about false discoveries when the number of genes is very, very large. So this is also something that we covered in the seminar 2 weeks ago, but I like to introduce another time. So if the data are generated from the null hypothesis, or if we believe that the null hypothesis is true, in that case, the p-value should follow a uniform distribution from 0 to 1, which means that the p-value can have the same chance to take any value between 0 and 1. So in that case, if we set the significant level threshold as 0.05, then even though all the genes are not differentially expressed genes, even though all the genes have mu1 equals to mu2, even though this is the truth, we still have 5% of the p-values smaller than the 0.05 threshold. So which means that with, for example, 10,000 genes, the expected number of false positives is 500 when these 10,000 genes are all non-DE genes, because 5% of them will have p-value smaller or equal than 0.05. So if we only look at one gene, it's okay. But if we look at 10,000 genes together, we will make a large number of false discoveries. So if we, for example, if we want to treat the one gene as some indicator for example, for medical diagnostic, in that case, such large number of false discoveries will be a very large problem. So we want to get rid of these false discoveries. And how can we do that? So in our last seminar, we introduced two criteria for controlling the false discoveries. One is called the false discovery rate, and another is called family-wise error rate. So this time, we mainly focus on the false discovery rate, which is defined as the expectation of the number of false discoveries over the number of total discoveries. So for example, if we make 500 discoveries and all of them are false discoveries, then in this case, the false discovery proportion is 1. Or if we have 100 false discoveries in this 500, then the false discovery proportion will be 20%. And the false discovery rate is expectation of this proportion. So by controlling the false discovery rates, we want to make sure that when we make some discoveries, even though we may make some false discoveries, we want to make sure that the proportion of those false discoveries is smaller than a predefined threshold, for example, 0.05. And a very famous procedure to control the false discovery rate is called the BH procedure, Benjamin-Hochberg procedure. So the procedure to controlling false discovery rate is as follows. It has 2 steps. The first step is to order all the p-values from smallest to largest. So if we have D p-values from D genes, so here this is a cartoon for the BH procedure. So this time this is different from the previous example for D genes. So here, each column is a sample and each row is a gene, and the black rectangles are from one condition, and the white rectangles are from another condition. So here, for each row is a gene, and we summarize each row into a p-value, and as we have D different genes, we have D different p-values. The BH procedure first order these P1 to PD into P parenthesis 1 to P parenthesis D, and then we compare the I's ordered P value Pi to 0.05 times I over D, and reject the I's null hypothesis if Pi smaller or equals to 0.05 times I over D. So this is the BH procedure, and it can, by doing this, it can control this false discovery rate. And so we can see that the BH, in fact, it gives a cutoff on the p-values to control the false discovery rate. And do we have any questions about the false discovery rate and false discovery rate control? So in fact, you don't need to really remember all these BH procedures, but you only need to know, so it is something that can control the false discovery rate given some p-values.
I had a question about the alpha value of 0.05.
Yeah.
Is that just a set number, or where is that coming from?
I think
that's a very good question. So Xinzhou, maybe I can add one thing before you continue. This is just someone, if you have heard of his name and his stuff, I think most of those practices we use nowadays were from him. It's Ron Fisher. So he was someone who lived 100 years ago. And so I think he passed away around 1960s. And so he just said, okay, to me, 5% seems to be a small enough probability. That's just where the 5% came from. But if you think, okay, 5% is not small enough, you can set alpha to 1% or 0.1%. So alpha itself is just an arbitrary number, which you consider as small probability.
Okay, thank you.
Yeah, so Xinzhou, please continue.
Yeah, I think Jessica has given a very good explanation for the alpha. In fact, this is really arbitrary, and you can always select your own alpha. But in almost all cases, people use 5% as a threshold, just as something conventional. And finally, let's go to the p-value free part. Yeah. So by now we have introduced how can we use the p-values to control the false discovery rate. We can use the for example, we can first use a 2-sample t-test to calculate the p-value for each gene, and then we can use the BH procedure to make some correction on the p-values so that we can control the false discovery rate. However, we find that there are some limitations for these p-value based methods for false discovery rate control, and we find that the p-values either requires the distributional assumptions or large number of replicates, here replicate means samples for each condition. So we first look at the distributional assumptions. So the two sample t-test requires that the values or the measurements come from the normal distribution. It is very strong assumption, in fact, and in most cases for most biological data, especially when the number of patients is very small, we cannot really know what distribution the measurements comes from. And we may make wrong distributional assumptions if we just use one test, for example, the t-test. This is for some parametric ways of doing tests. And there are also some non-parametric tests, but for those tests, for example, the Wilcoxon rank test, they require the large number of replicates, which is not available in the high throughput biological data. So we can see that there are some limitations for the p-values. And when we use the p-values to control the false discovery rate, the results will be questionable if the assumptions of the p-values are violated. And we also use some data analysis to validate these claims. So to show that the p-values become invalid and the FDR control becomes questionable when we have bad model assumptions. And to solve this problem, we propose our clipper, which is a method that does not use p-values and it does not assume any parametric distributions. And it also does not require many replicates. So it has two components. First, instead of the p-values, which is calculated possible by some model assumptions, it summarizes the values from the two conditions into something we call contrast scores, which indicate how different the two conditions are for that feature. And then with the contrast scores for all the features, we set a cutoff on the contrast scores and get the contrast scores greater than that threshold as discoveries. And it is why we call it clipper. So because we only want a small proportion of features, get rid of the other one. So it is like a clipper. And another reason is that we are in LA and we have a basketball team called Los Angeles Clippers. And for this, we call our method clipper. And we show that clipper is very robust to different kinds of data distributions and different numbers of replicates. And we also find that clipper is robust to outliers, which means that even when we have some extremely large values in our data set, which are outliers, we can still get good false discovery rate control using clipper. Okay, that's all for the background of our project. And do we have any questions? Okay, if not, I will go to the method, how you implement clipper to control the false discovery rate. I will mainly use some cartoons to do this. So here I may still introduce some mathematical notations which may be essential for understanding our method. But I think it's still okay if you feel it's too complicated. So let's look at the data structure first. You have two conditions. experimental condition and the background condition, and we call these two matrix X and Y. So for the matrix X, each row is a feature, and each column is a replicate. So we have M replicate for experimental condition, and we have N replicates for the background condition. So we call the expectation of each row as mu xj for experimental condition and mu yj for background condition. A feature j is interesting if mu xj, which is the expectation of this, is greater than the expectation of this. Or if we call a feature as differential, interesting in a differential analysis if mu xj not equal to mu yj. So maybe I can give you some time to look at these notations and feel free to ask questions if you have.
So maybe Xinzhou, you can explain a little about what you mean by the yi symbol, the expectation. What does that mean here?
You mean this?
Yeah, the expectation.
The expectation is, I think, it is so we consider that all the replicates from the same feature follows the same distribution, and the mu xj is the expectation of that distribution, or we can just consider it as mean of something like the mean of these values. Do you think it's clear?
Yeah. So basically, we're imagining that if we repeat the measurements for infinite number of times, what will be that average? That average will be what we call the expectation. So that's the underlying truth you are really interested about. And you think anything, so the reason your measurements x1, xj1 to xjm are not equal to that mu xj, the expectation, is simply because your experiments are not 100% accurate. There's randomness, there's measurement randomness in your experiments that causes these m values to be a little different from that expectation. But your interest is in that expectation.
Yes, so it is a truth.
Yeah.
Mu xj and mu yj are something that we don't really know, but we believe it is some truth, and we want to analyze about the truth, whether it is different between the two conditions. Okay, and the Clipper, the implementation of Clipper is different for 3 different analysis tasks. The enrichment analysis with equal number of replicates for the 2 conditions. So for example, m equals to n means we have the same number of columns for the two conditions. And we also have enrichment analysis with m not equal to n. And we also have differential analysis. And before introducing the cartoon, I would still like to introduce some summary statistics. So first, if we look at the enrichment analysis when m equals to n, we define contrast scores as the t-diff of xj and yj, where t-diff is x bar minus p-diff xy is x bar minus y bar. So here, so in this case, if we look, the contrast score of feature j is the difference in means between the 2 conditions. So for example, if we have these two, if j equals to m, we look at the first feature or first row of these 2 matrices, the contrast score is the difference in means between the 2 conditions. It's very, very simple, just the difference in the 2 means of these two conditions. Or if we look at the cartoon illustration, so here in this example, we have one experimental condition and one background condition. And this is one feature and this is another feature. For this one feature, if we calculate the difference in means, as we only have the one feature for, sorry, one replicate for each condition, the difference in means is just a difference between the two values. So the difference contrast score is just 10 minus 0 equals to 10. So this is the difference contrast score. Another contrast score which is alternative for the difference contrast score is called the maximum contrast score. The maximum contrast score is defined as this. Still with X bar and Y bar, it is T max XY is X bar if X bar is greater than Y bar or equals to negative Y bar if Y bar is greater than X bar. Here sign means sign function returns positive 1 if X bar minus Y bar greater than 0 and returns negative 1 if what's inside is smaller than 0. So in this example, as 10 is greater than 0, the maximum contrast score is 10. And if we look at another uninteresting feature with two measurements as 1 and 2, the difference contrast score is 1 minus 2 equal to negative 1. And the maximum contrast score is so first we look at the maximum of the two values. The maximum is 2, and then we decide the sign of the contrast score. As the background condition is greater than the experimental condition, which means that X bar minus Y bar is smaller than 0. So in this case, sine X bar minus Y bar becomes negative 1. So this will be negative 1 times the maximum of these two values. So it will be negative 1 times 2. So it will be negative 2 for the uninteresting feature. And this is for the enrichment analysis with m equal to n. And do we have any questions about the calculation of the contrast scores? So if not, then we will threshold the contrast scores. So for example, if we only use the maximum contrast scores, we will have 10 for the first feature and negative 2 for the second feature. And then we will have many features. So we will have many contrast scores. And then we will use this mathematical formula to threshold the contrast scores. So if we don't look at the mathematical formula, but only look at this figure, so from the D different features or D different genes, we will have the contrast scores from C1 to CD. And if this is the distribution of C1 to CD, we will expect that if a gene is uninteresting, then for those uninteresting genes, the distribution of the contrast score will be something symmetric around 0. And the interesting genes will have large contrast scores. So for example, this interesting gene has large contrast scores, and this uninteresting gene has small contrast scores. So we hope that all this part about the uninteresting part, and this large tail is for the interesting features. And we cut a threshold here, and we treat then this part as interesting discoveries. So the thresholding part of the clipper is just to selecting those extremely large contrast scores compared to those uninteresting features. So do we have any questions? So if not, I will go to the enrichment analysis with m not equals to n. And in this example, we will do some permutations. So this is still a cartoon illustration. And in this example, we have, this is the original feature. In this example, we have two features, sorry, two replicates from the experimental condition and one replicate from the background condition. And if we still calculate the degree of, and sorry, I will introduce degree of interestingness later. So the permutation means that we permute the three values. We change the order of the three values, but we still keep the first two as the experimental condition and the last one as the background condition. So the original, if we look at the original feature, it is interesting because the values in the experimental condition are much larger than the background condition. However, after the permutation, this has changed. For example, in the first permutation, the values, the average values of the experimental condition is not so different from the background condition. So, which means that by doing the permutation, we want to change the relationship between the experimental condition and background condition, but still keeps the values. So from 10.6.0, we can permute into 10.0.6 and 0.6.10. These two different kind of permutations. And for the origin and two permutations, we want to calculate something called the degree of interestingness. And the degree of interestingness is still the difference in means between the two conditions. So for the original one, the difference in means is 8 minus 0 equals to 8. For the permutation 1, the difference in means is 5 minus 6 equals to -1. And for the permutation 2, the difference in means is 3 minus 10, which is equal to -7. And finally, we will summarize these values, these degrees of interestingness, into contrast scores for each feature. And the summarize of the contrast scores will, we will still have maximum contrast scores and difference contrast scores. The maximum is the maximum of all the degrees of interestingness, and the sign will be positive if it comes from the original, or negative if the maximum comes from the permutations. And the difference contrast score will be the difference between the largest degrees of interestingness and the second largest degrees of interestingness, which is 8 minus -1, which is 9. And if we look at another uninteresting feature, so for example, this one, we will see that after the same calculation, we will have small contrast scores for an uninteresting feature, but large contrast scores for an interesting feature. And finally, we will still do some cutoffs on those contrast scores, which is very similar to the one that I introduced previously. And finally, with all these procedures, we can summarize the measurements from the two conditions as contrast scores, and then use contrast scores to control the false discovery rate without using p-values. And we used many simulation analysis and real data analysis to validate our results, to show that it is really important to get rid of those p-value based methods because those p-value methods are questionable. So maybe I can just skip this and go to the discussion. So to summarize, our method get rid of the use of p-values, and we have broad applications in high throughput biological data using the concept of contrast scores. And we also want to voice the importance of validating the FDR control, because FDR control is assumed but rarely validated in most bioinformatics methods. And I think that's all for my talk. And do you have any questions about after all these?
So I think one question I can ask the students, and some of you may volunteer to answer, is why do we really need simulations to verify the performance of those methods? I think that's a very general question for research in this field. We do a lot of simulation, but probably the students are not very familiar with what we mean by simulation. So can you raise your hand if you know what we mean by simulation? Xinzhou, you see that the students are not familiar with this term. Probably you can explain this a little bit, what we mean by simulation, by doing simulation.
Yeah, in fact, I didn't include the results about the simulation because I think this may be hard to understand. But
probably, can you actually open your RStudio to do a quick demo for them? Like you generate data from, say, a standard normal distribution, and then you use the data to calculate the sample mean, and then you check whether the sample mean are around the true mean after you repeat your simulation. Yeah, that's actually one simple example of what we mean by simulation.
Yeah, I think. Yes, and yes, maybe I can just use the example that I used for the 2 weeks ago. Yeah.
Please go ahead. Yeah, because not everyone was there.
Oh, yes, maybe I can. Maybe I should search for that. I may forget where I put. Oh, so what's the name of the CSUN?
CSUN.
CSUN. Okay, CSUN. Okay. IPs. So this is the one demo. Can you see my screen?
Yes.
Okay.
Yeah.
So this is a demo that I used for the seminar 2 weeks ago, and this includes the data simulation part. So in fact, we want to validate some of the results based on simulation because we only know the truth in simulation. In real data sets, we don't really know the truth. So we don't know whether our conclusion is correct or not. But in simulation, we can simulate the truth. So for example, here we can simulate 1,000 genes. And we have 2 conditions, the experimental condition and the negative control condition. And in simulation, we can know what is true D genes and what are the true non-D genes. For example, here I can just make the first 800 of the 10,000 genes as non-DE genes, and the last 200 genes as true DE genes. And then I can have some idea of different methods based on these truths. So for example, I use this to simulate X, which is the experimental condition, and simulate Y from the background condition. And if we look at the first several rows of X and the first several rows of Y, we will see that they are very similar. But if we look at the last several rows and last several rows of X and Y, we can see that the X values are much larger than the Y values. So this should be the case because it is all these values are simulated from our truths. So we know the true DE genes and we know the true non-DE genes. And then we can also look at the p-values. So here I just use a two-sample t-test to calculate the p-values, and then we can look at the histogram of the p-values. So here is a histogram of all the p-values, and we can see it is uniformly distributed. So from this simulation, it further validates that if the null hypothesis is true, the p-values should follow a uniform distribution from 0 to 1. And yeah.
I had a quick question.
Yeah.
I've heard of this term called like bootstrapping before, but I wasn't sure what it is. Is that like anything similar to what this is?
No.
No, bootstrap, yeah, I can answer this question. So Brandon, which class did you learn this from? I'm just curious.
It wasn't from a class. It was like, well, it was like an online sort of coding thing that I did.
Okay. Yeah, so bootstrap is actually something which seems to be quite simple, but in fact, its underlying justification is very complicated. So by bootstrap, what you mean is that you try to do sampling, draw samples from your current data so that you can have what you call bootstrap data or bootstrap sample that you can use to make, I'll not use jargon, to actually talk about the quality of an estimate you obtain from your original sample. Let's say, just say you have your original data or your sample from which you compute an average. And you want to know how close this average is to the population mean you are interested in. So to do that, if you don't know the mathematics or anything you can derive mathematically, Bootstrap provides a computational tool. What you do is that you pretend that this sample, your data, is the population. And from that, you are going to draw new bootstrap samples as if you were drawing original sample from the population. So you are going to use bootstrap to mimic the sampling of your original sample from the population. Then you can say, when you do bootstrap, you're treating each data point in your original sample as just possible values you could draw. Okay, and they have equal probabilities. You can draw your data points with replacement. Then in each bootstrap sample, you can compute a mean, a sample mean. So let's say you do bootstrap for 1,000 times, you will have 1,000 bootstrap mean, and you will check how these 1,000 values are close to your sample mean of the original sample. So you think this uncertainty captured by bootstrap can let you use to infer the uncertainty of your original sample's mean to the population mean. I hope that makes sense.
Okay, thank you.
Yeah.
Yeah. Yeah, and we can, yeah, from this example, you can see that by the simulation, we can validate that the uniform distribution of the p-values by looking at the histogram or looking at the proportion of the p-values, which is more than or equal than 0.05. And then we can also use different p-value correction method, multiple testing correction methods, including the the BH method that I introduced before, so that by using simulation, we can know the truth, so that we can know the performance of different methods, or you can use simulation to validate some theoretical results. Okay. And do we have any other questions?
So Xinzhou, Emma just gave you a thumb up.
Okay.
Yeah. I would say, Xinzhou, could you recommend some courses for them offered by our department? Which courses do you think are well taught? Based on your TA experience.
Course, I think I think
or you can recommend some lecturers, like the professors' names, who you think are good teachers.
Yeah, I think the stats. So are we all from the stats department? No.
No. Many of them are in other majors.
Okay. I think
Yeah.
stat 10 will be, or if not from our department, it should be stat 13. I think that will be very important course for the introduction of the statistics.
Okay. Do you recommend any instructor for that course? Because I think we have several people who teach the same course.
Yes.
Okay, so Brandon said he really likes Miles.
Miles. I haven't worked with Miles.
Okay.
Yet. And yeah. So I didn't work with many lectures for stat 13, so I don't really know. But I think Rob is very good. Very good. Yeah. I think he is the best lecturer I have ever worked with.
I see. Yeah, I can actually see that from my communication with him. So he's Robert Good. Yeah.
Robert Good, yes.
Yeah, so Xinzhou, you think stats 13 is good? Yeah, because I don't teach lower division courses. So to me, I'm not very clear about the distinctions between stat 10 and stat 13.
I think they're actually very similar. Yeah.
And I think stats 20 is for R programming, right?
Not sure.
Yeah, I taught that for once, but I don't know if it's offered every quarter.
Yeah. And I think stats 1.1c is very important for the application of the knowledge of the statistics. The whole course is about applications and not much theoretical parts, but it may be very interesting if you have taken some theoretical courses. Stats 1.1c.
Yeah, I see. So yeah, I would say stats 100B with Nicholas Crystal. Yeah, I know his course pretty well because I taught 100B for 3 times myself. And I think Nicholas teaches this in a very deep way. Although it may seem a little intimidating in the beginning, especially I think his exam problems are very hard. He actually requires people to, do multivariate things. So to do that, you need to know multivariate calculus. So that you are comfortable with vectors, matrices, those kind of things. But I think Nicholas is a very, very approachable professor. And so what's amazing to me is that he has office hours all the time, as long as he's in the office. Yeah, he really cares about his students. And also, although the exam problems are very difficult, but he curved the grade. So that's why as long as you're doing well in your class, you don't need to worry too much about the grades. Yeah. So that's something I think is very good to learn. And if you already know that those matrices, vectors, multivariate calculus, multivariate statistics are important, then you will have strong motivation to really understand them. And that's a very strong foundation for the 100C, which covers linear model, right? You need to know the matrix notations to deal with linear model in a very concise way. Okay, so if we don't have further questions, I think we can conclude for today, and we will meet again in 2 weeks. So at 1 p.m. So next time we'll make sure that our announcement has the time correct. Okay, thank you.
Thank you.
Thank you, everyone. Thanks to Xinzhou for the presentation. Thank you. So yeah, we'll stop here. Bye. Bye.